Good morning, Algebra 2. Your teacher, Mr. Woe here. And as usual, are you with me? All right, today we're going to look at section 12-2, dealing with geometric sequences. Now, our essential question today is how can you define a geometric sequence algebraically? All right, what I'd like you to do first is take a moment, do the Explore A through J, and then come on back to the video. All right, A through J is just taking a little bit of time and investigating geometric sequences. Here is our problem. Again, as a tree grows, limbs branch off of the trunk, then smaller limbs branch off these limbs, and each branch splits off into smaller and smaller copies of itself, the same way throughout the entire tree. A mathematical object called a fractal tree represents this growth. So here is a picture of a fractal tree. Again, things I have here is all filled in the blank, but I think the main focus is the table at the bottom, okay? Again, if you worked all this stuff out, you should have got pretty much everything that's here. But again, a couple things I want to focus on here is that deals with a geometric sequence. This is an example of a geometric sequence. Again, the first column is the term of the sequence. This is just like we did with arithmetic sequences. And here is your geometric sequence. 1, 2, 4, 8, 16, 32, 64. Okay? Now again, all that comes from an application of all up here. Okay? Or as a matter of fact, it starts from right here. So again, let's go to the next page. And again, A through J, all we had to do is take the time and work this out. I'll let you guys study on your own. A couple things I want to draw your attention to is two things. Let me get my green pen. Two things I want to draw your attention to. This and the graph. Now when we did section 13-1, well actually 12-1, when we dealt with arithmetic sequences, we got a linear function. Now in a geometric sequence, we're going to get an exponential function or a power function. A little bit different. But what we're going to do, just like we did in arithmetic sequences, we have to create an equation. This is what we're trying to find out. This equation right here, n of s equals 2 to the s power. This is what we're trying to find. And all this page sets it up. All right? Now I'm going to show you how to do this stuff. It's really not that difficult. All right, go to the next page. Again, I'm not interested in this part. This one is going to be, this one is increasing. This one would have been an example of a decreasing. I'm not interested in that. All right, let's go to how to do this stuff. Ready? Top of the page. Again, there's some things in here I'm just busy work. We don't need that. Again, at the top of the page, what I highlighted in blue should be the best to study. A sequence is a set of numbers related to a common rule, just like what we did in the last section. We got to have a common rule. In section 12-1, our common rule was a common difference. Each term, from one term to the next term, we notice that each of the terms either has increased by the same value or decreased by the same value. But now in a geometric sequence, again, from one term to the next term, you're going to have, instead of a common difference, you're going to have a common ratio. And that's either going to be a multiplication or a division. So this constant ratio is called the common ratio. And our job is put it in what is called explicit form. Again, explicit form is, I think that's more important than the recursive rule. Okay, so again, If I go back like here, this is an explicit form. That's what we're going to be focusing on. All right, I'm not interested in the recursive rule, so when it gets time to do homework, don't worry about it. All right, up here are the formulas. You may not see it, so let's just go to the next page. So again, at this page right here, again, this up here is your two, these are both the same thing, okay? What I showed you on the very first page, that's this part, but we're also can see it in this way. Now again, this is the explicit form of a geometric sequence. A sub n means it has to deal with what term we're dealing with, okay? What we're trying to find. A sub 1 is the first term of your sequence. Your R is your common ratio. So by example, let's look at the year term number 4. Again, the way the problem is set up, these are our terms. Now this one starts off with the term of 0. Okay, so this is the first term. So the first term of our sequence is 1/27th. The second term of our sequence is 1/9. The third term of our sequence is 1/3. Now again, I am not a big fan of how they start off with 0. Don't let that confuse you. Just remember that the 0 here means that's the first term of the sequence. 1/9 is the second term. 1/3 is the third term. Okay, you can figure that out. Now what I focused on here now is looking at your sequence of numbers. And you're going to notice from 1 to 3, it's been a product of 3. 3 to 9 is a product of 3. And 9 to 27, it's a product of 3. That tells me that this entire sequence has increasing from each term to, from this term to this term, it's been increasing by a factor of 3. So that is your common ratio. And we notice that our first term is 1/27. So if we set up our problem, okay, we know the first term is 1/27th. We know our common ratio is 3. Here is our equation. Now, this statement right here is letting us know that we started off our first term to be a 0. Okay? So in other words, if I were to take and say, well, if I let n become 0 here, 3 to the 0 power is 1. 1 times 1/27th gives me 1/27th. All right? Try to remember that, because some problems are going to start off with the first term, this being the first term, 0 be representing the first term, and there will be examples that won't. All right, what I want you to do now is take a moment and pause the video and do number 5 on the year term. All right, we're back. Again, here is the bottom row is your sequence of numbers. Again, the first thing you'll need to do is see if this has a common ratio. Well, this one does have a common ratio of a product of 10. So that tells us our common ratio is 10. And our first term of our sequence is 0.001. All right. Now again, I'm going to keep it as a decimal here for the first term. You may also do this. It's no big deal. All right, so here, again, is your equation. There's your first term multiplied times the common ratio raised to the n. And once again, we're going to let n start at 0. Even though this represents 0, represents 1, that just means that this is the first term. So if I let n become 0 here, 10 to the 0 is always 1, and 1 times 0.001 will give me the first term of 0.01. Let n become 1 now. 10 times 0.001 gives you 0.01. You'll see it. All right, I can show you on a calculator. Ready? 0.001 times 10 to the first power is 0.01. 10, or actually, let's do it this way. 0.1, actually, come on now, let's set it up. 0.1, let's do correctly now 0.001 times 10 to the second term. The 2 is the second term. In this case, don't ignore that. Even though it says 3, this is, again, this is going to be the third term, okay, or whatever. You'll see the picture when you get to it. Do your math, you get 0.1. All right? So the big thing to use are these guys up here. These are your explicit rules for a geometric sequence. And you got to make sure from each of these terms there is a common factor being involved. Okay? That's called the common ratio. I think I got a word problem here. Nope, let's try another one. This one's a little bit, this one involves graphing. Again, the way the problem is set up here, do not let this confuse you. This is just set up as a recursive rule. You don't have to work, don't let that fret you, okay? It means nothing. You'll see why in a second. This right here is your common ratio, okay? And over here, this tells us that the first term of this sequence is going to be 16. So I know when x is 0, okay, y is going to be 16. That's where they get here. That's all. Now the next thing we need to know here is we already know this has a common ratio of 0.5. So that means from this term to this term, we're multiplying it by 0.5. From this term to this term, we're multiplying it by 0.5. Or in other words, we're just taking half of it. So the half of 16 is 8, and half of 8 is 4, and half of 4 is 2. So don't let this throw you off, okay? This is the common ratio. This right here represents the first term of the geometric sequence. That's this guy right here. You with me? All right, let's do your turn number 6. I think that would be a good one to work out, okay? We see right off the bat, our common ratio is 3. I'm sorry. The first term of our sequence is 3. Well, again, let's do it this way. Let's make sure we have our formula written down so you guys can see it. A sub n equals the first term of the sequence times r to the n. Well, I see my first term of our sequence is going to be 3. So I know when this is going to be my first term of the sequence. Okay. You can check that by letting n become 1. So n minus 1, 1 minus 1 is 0, and 2 to the 0 is 1, and 1 times 3 is 3. Okay, we don't even have to worry about this anymore, okay? We already know that this has a common factor of 2. So we know that's going to be multiplied by 2. So that becomes 6. Well, you can check. All right, so 2 to the 2 minus 1 is 2. 2 times 3 is 6. And this guy right here is going to be multiplied again by 2. You get 12. All right, so over here graphing it, very simple. You can use the t-graph if you like. We know when n is 1, y is going to be 3. Boom. We know by letting n become 2, this will be 6. Let n become 3, it becomes 12. Okay, this becomes 24. So when n is 4, y is 20. It's way up here, so you're going to get an idea that this is going to be an exponential type function. Really easy stuff, guys. Don't let it confuse you. And I don't know if I have any other ones here. Oh, yes, I do. This one will be pretty cool. A particular type of bacteria divides into 2 new bacteria every 20 minutes. So every 20 minutes, we get 2 new bacteria. The scientist growing the bacteria in a laboratory begins with 200 bacteria. How many bacteria are present 4 hours later? So in other words, we're going to have 12 increments of 20 increments, 20-minute increments. Right, where we're going to go with this? Well, right off the bat, we know right at the beginning, okay, the laboratory begins with 200 bacteria. So we started off at 200. Then it says it divides into two new okay? That's a play on words, okay? It just means I'm going from 200 and after 20 minutes it's doubled. That's what it means. The particular type of bacteria divides into two new bacteria. It doubles. So from here to here, we got a multiplication of 2. From here to here, multiplication of 2. From here to here, multiplication of 2. It's doubling itself. So with that said and done, the common ratio is 2. We know that we're going to figure out how many bacteria are present 4 hours later. But we already know that 3 20-minute increments make up 1 hour, and we're going to do 4 hours. So 3 times 4 is 12, so we have to figure out what n is 12 is. So setting the problem up, okay, here's our explicit form of a geometric sequence. And again, we want to find how many bacteria are present after 4 hours. You take your common ratio, you take your first term, which is 200, multiply it times 2 to the n. Now this one, you'll probably need to use your calculator. So it'll be 200 multiplied by 2 raised to the 12th power, enter, and you get 819 200 bacteria. All right. So once you guys got that, you'll have no problem. First, see if it's a geometric sequence, and then go from there. Okay. All right. I think that was a good video. Again, if you have any questions, you know how to get a hold of me. All right. Good luck. Catch you later.